All right. Mrs. Gregory, you look terrific as usual. I am so excited to help on test hits.
Dude, you got to fix your collar because you know this is going out to the World Wide Web, and you want to look professional.
Not to put too much pressure on me.
Right.
Okay. Well, welcome to the Chapter 5 Part A test hits.
So the first half of Chapter 5, which was actually the very beginning of the chapter, and then we flipped all the way over to Section 3. We're doing all the quantum stuff and what the electrons are doing in terms of producing the different colors of light and so on.
Yeah. This is kind of out of order from the textbook.
Right. But what we did on the test hints was we put the first 20 questions are the part of the chapter that we did this time, and that's what we're going to cover on this test. It should be pretty straightforward because we only have 20 things to work on for this test.
We're going straight off the test hints, so if you haven't printed one out, you really better do that.
Right, or look at them online, and you know what, Mr. Sussman, I think, since we did this a little bit differently this time, we should acknowledge the fact that the dedicated and motivated students out there are the ones that are on Moodle right now, watching this fantastic presentation. So
kudos to you all.
Good job for going above and beyond what your classmates are doing.
Exactly.
You're going to be so awesome when it gets to the test.
Rock the test.
All right, let's go number 1.
All right. Question number 1 is the location of the subatomic particles in the Bohr model of the atom. It definitely says Bohr model. So I don't want to hear anything about plum pudding and blueberry muffins. This is Bohr model.
Or chocolate chip cookies.
Or chocolate chip cookies. It's protons, neutrons, and electrons, and where they are.
Yeah, and it kind of focuses in on what the electrons are doing. And remember, the Bohr model is the one that you guys are all like, okay, we've got the nucleus here with parts in it, and you're used to seeing these circles. And what's in the circles? The electrons. So that's what Bohr was focusing in on. The question will be something like describing where the electrons are in relation to the nucleus and what those electrons are doing. Okay, ready for number 2?
You betcha.
Alrighty, test hint number 2 says how Bohr described the orbit's movement energy of an electron. So this is very similar to question number 1. But what we're adding in this time is the energy part. So if an electron is here, hopefully you guys can see this on the video. If an electron is here in one of these rings or energy levels, what do we know, Mr. Sussman, about that electron as it's in that energy level?
It has a fixed position around the nucleus, meaning it's not a position, but a fixed energy. It travels in a particular path. The entire time it's on this second energy level, it has that one energy.
Right. So like the stair steps thing, when we talked further in the chapter about the electrons being able to jump and we did all those labs, at a level, energy constant, that's the key.
Energy is the same. If it jumps out, it now has a constant energy on this level. Or if we're talking about an electron that lives here, it has one energy going around that level.
Okay. Number 3, it's all you.
Oh, gotcha. Number 3 says what, specifically, happens to energy when an electron moves from a lower to a higher energy level, which brings us back to this electron jumping out to this energy level.
So it's going to go from one spot out, we're talking about, or to whatever specific energy level, but it's going up, not down. And we've been emphasizing a lot, where do we get that bright line spectrum? And we're talking about, okay, the electrons jump back, they spit out that light. This one is asking about going the other way. So what's the electron doing when it goes up? Do we want to tell them?
I will. It's absorbing energy. It is going to absorb a photon of energy and jump outward. That would produce what kind of spectrum?
An absorption spectrum?
Absorption. That's exactly correct.
Right.
Next one.
Okay, number 4. The test hint says the relative wavelengths from shortest to longest for visible light. Shortest to longest. You all know Roy G. Biv, but
But
Roy G. Biv wavelength.
Roy G. Biv goes longest to shortest. Red light has the longest wavelength. And the question is, shortest to longest or longest to shortest?
If they need to know where are the shorter wavelengths.
So they need to make sure they slow down and they read the question correctly.
Grab our model. Okay, so where in the spectrum are these shorter wavelengths? Over here on the purple end. And if your parents got you this toy when you were little and they prepared you for your study of quantum physics,
It's probably still crusty with drool and boogers.
it probably is. Your mom's probably got it saved in the attic. The little ring is the one that's going to have the shorter wavelength and be on the purple end of the spectrum. Okay, let's go.
All right.
Number 5. Is that you or me? How are frequency and wavelength of light related? Your chemistry teachers love you so much. We know you don't think that sometimes, but we are so nice that we put all of the equations that you're going to need right in the footer on the test page.
But we're not going to tell the other students.
No.
Only the ones who
Only
visited
people who log in.
Moodle know that.
You can see it's right at the bottom of the page, every equation and constant you're going to need. You need to know what to do with them. So when we're asking you how are frequency and wavelength of light related, let's just give you a hint as to how this question would be worded from the test. It says, how are the frequency and wavelength of light related? So, go for it.
So here's red light. It has a long frequency or a long wavelength and a relatively low frequency. If we look at green light,
Thank you, I will demonstrate
if
that.
we look at green light, it has a shorter wavelength and a higher frequency. In math class, you called this an inverse relationship. One variable goes up, the other goes down. One variable goes down, the other one goes up.
Right. So as long as you understand that, this question should be easy. All right, you, number 6.
6. The test hint says how to calculate the wavelength of a wave when given the speed of light, c,
Yes, C in the equation.
and frequency.
Okay. And in this particular question, we're not asking you to actually work out the problem. We're asking you to identify which answer choice shows the work, which we keep bugging you about, shows the work set up so that if you did calculate it out, you would be getting the right answer for wavelength. And go back to your quantum ladder worksheet, because we did some practice problems there, and look at the sample problems in the notes and PowerPoints.
You need to be able to show us how you solve that equation, how you manipulate that equation, c equals lambda times frequency, to solve for the variable that we're asking you to solve for.
Right. Okay. Number 7, the kind of spectrum produced by a gas discharge tube. So this was the lab we did with the rainbow glasses. We had the power supply out, and we were putting those gas tubes in the power supply. We turned it on, we zapped those electrons with energy, and they glowed. Those of you who have been watching the videos that we have posted on Moodle to help you, Mr. Bergman and Mr. Sams demonstrate that for you again. And there's a couple different places on our Moodle pages where you can see that. So, what kind of a spectrum is that? Yeah, what kind of a spectrum is that?
If you're looking at the lamp that's lit up through your spectroscopic goggles of science and you see this,
Yeah. What? Oh,
and
I
you
see this
see
pattern
this,
clearly.
what kind of spectrum are you looking at?
Are there choices?